Solutions. Solutions are homogeneous mixtures of substances, for example, iced tea or lemonade. They have two parts to them. There's a solute and there's a solvent. The solute is the piece that dissolves, it hides. The solvent is the piece that makes it dissolve. So it's considered the major component of the solution. So you have a picture of coffee and cream, and there's a picture of sugar and water. When you look at the coffee and the cream, you realize that the cream is going to dissolve and pretty much blend equally into the coffee. And the sugar will do the same. It will dissolve inside. So which piece is the sugar in the cream? Is it the solute or the solvent? It's going to dissolve, so it's the solute. The water and the coffee will be the solvent. Very often it's referred to water as the universal solvent because it dissolves a lot of things. It doesn't dissolve everything, but it dissolves a lot of things. So water is considered the universal solvent. Now, this is a picture of water with KBr, which is potassium bromide, and it is dissolved in the water. So you see how the purple and the red are equally dispersed inside the water. This, now we add some salt, and you have salt and bromine in there, and then you have it separated out. So we added them together. They don't chemically react, they just make a solution, they make a mixture. You can't even see these particles in the water. That's what happens in a solution. Now, solutions don't necessarily have to be liquid and solid. They could be gas and gas, just like air. Nitrogen and oxygen are in the air. You don't see them. They're equally mixed. They are floating around in our air along with our greenhouse gases. And sometimes the solution can be a gas to a liquid. So you have soda, for example. These little water molecules and the carbon dioxide are equally mixed, but sometimes the carbon dioxide doesn't want to stay in there, so it tries to escape, and you can hear the gas trying to escape. So you know that solutions are mixtures because they keep their properties and they can separate them physically. All right, characteristics of your solution. There's only one type of substance it appears like. Really, there's not. There's really two, but it looks like there's one type of substance, or it could be three, just like the example we saw earlier. So this is your solute, and that's your solvent, and we put them together, we have a solution, and they're pretty much equally dispersed. The solute is equally spread out among the solvent, so everything is uniform. So the first sip of your iced tea will be the same as the last sip, provided that the solute dissolved fully. Sometimes you put too much sugar in there, and it's stuck at the bottom because it didn't dissolve completely. Characteristics. They appear like they're one type of substance, they're equally spread out, and all parts of the solution are uniform. Now, we can change the solubility if we wanted to, and sometimes things aren't even soluble. Well, solubility basically just means how much solute dissolves in a certain amount of solvent under specific conditions. So if you look at this picture right here, showing you a picture of sand in water. Is that soluble? Can that dissolve in the water? Well, stir that sand all day long and you're not going to get the sand to disappear. It's not going to dissolve. So we don't say it's soluble, we say it's insoluble. Here is salt and water. You stir that up, you let it sit for hours, the salt will eventually dissolve in the water and you get salt water. You can separate them again. How would you separate out the salt and the water? You let the water evaporate, the salt is left behind. All right, well, what is dissolving? What happens when something dissolves? Basically, the solvent has big muscles and it pulls the solute away. No, really what happens is that they separate and they make ions. And how does that happen? Well, little by little, the solute kind of like sneaks in there and pulls it apart. You have a clump of salt on the table, it's not going to dissolve. But if you put water in it, it will dissolve because the Na and the Cl will eventually become ions in the water and they'll hide. So they'll get pulled away by the solvent. And they'll continue to do that until it's all completely dissolved. Once there's no more hiding spots, then you're going to see a clump of salt on the bottom because they have no place to hide. And then we say that the solution is super saturated. We took all the hiding spots. Add more water and more will dissolve. But it doesn't speed up the rate, which a lot of kids have a hard time understanding that. All right, the rate of dissolving. You stir it, you're going to make them dissolve faster. You crush it, you're going to make them dissolve faster. And you heat it, you'll make them dissolve faster because the molecules will move faster. You're increasing the surface area when you crush it, and you're making the solvent and everything in there move faster. So you're allowing things to find their hiding spots a lot quicker. Our solutions can be affected if you increase the temperature. If you increase the temperature with a solid, you're not going to do much. The solid can't be squished anymore. I'm sorry, I have to rephrase that because I got ahead of myself. If you increase the temperature, you're actually going to increase the solubility of the solid. So you're making everything go faster so it can increase its solubility. However, if you increase the temperature of a gas, well, gases move so fast. If you increase the temperature, you know what's going to happen? The gas is going to go away. It doesn't want to hide in the liquid. So the only way that you can change the solubility, make it in your favor for a gas, is by decreasing the temperature, because this is an inverse relationship. It's indirect. So that if the gas moves slower, it will dissolve. So you want cold soda. You make the soda too hot, all the gas disappeared and you don't have it anymore. Cold soda, it stays fresher longer, so we have to put it in the refrigerator. Otherwise, it gets flat quickly. All right, this is just a picture showing you about our ozone, and when we increase the temperature, the ozone will not sit still. It's going to leave. But if we decrease the temperature, lower temperatures, it will dissolve better. All right, your solutions, increasing pressure. There will be no change in the solid because the solid is squished as much as it could be. So the solubility rate stays the same. But if you want to increase the solubility of a gas, you push the solution together, and it's going to make the molecules get pushed together. So take a bottle of soda and really shake it up. You're going to increase the pressure because you're going to make the gas push together and move really fast. Once you open up the bottle of soda, it's going to explode because that gas wants to get out. You just made it want to move so quickly. You're lowering the pressure. Here's a picture of two gases in a chamber. When I push the chamber down, I push the molecules together, they start to dissolve better. But if I separated them, they're not going to dissolve because the gas wants to get going. The gas doesn't want to sit there. It wants to go away. All right. Concentrations of solutions. You make iced tea, and it doesn't taste that good. There's not a lot of stuff in it. We say that that is diluted because it doesn't have a lot of solute in it. So concentration is basically how much solute dissolved in the solution. So diluted something is not so good. It doesn't taste that good. There's not that much solute in it. It's very weak. If it's concentrated, it's way too much stuff in there. You should add water to it if it's concentrated. Like the stuff that you can get this Minute Maid in the freezer section, it's really, really concentrated, so you have to add water to it. And if you've ever made Campbell's chicken noodle soup, if you don't add water to it and you just put it in the microwave and you eat it, it's so gross because it's so concentrated. So you want to make sure you add 2 cups of water to your soup when you make it. Good idea, right? Specific concentrations. If something's unsaturated, the means it hasn't reached its level. It's not saturated. So you can put more in it. If something is saturated, that's it. Maximum amount, nothing left. It's saturated. There's 50 seats in the movie theater. We're only letting 50 people in. It's saturated. We got enough. If something is at its equilibrium, it's perfect. If somebody leaves, we're going to let one more in. But we can't let another person in because then they have to stand. So what would happen if your solution was saturated and you try to add more molecules? They'd have no place to hide. They'd have to stand. They would be lingering. So if you put too much sugar in your cup of water, it's never going to, you could stir that thing for days. It's never going to dissolve. The sugar will be left with no place to hide. It'll be there. And then you take a sip, bleh, too sugary. Way too much. It's what we call super saturated. All right, this is a solubility curve. So I'm going to use a pen with a different color. Let's use magenta to give us the idea of what's going on here. Temperature's on the bottom. And solute is on the side. Basically, this is telling you that your solute is dissolved in 100 grams of water. So how much solute can dissolve in 100 grams of water? If I had 200 grams of water, I could dissolve more, but we're only going to use 100 grams of water. So this is our constant for the experiment. So if I have NaCl and I make the temperature at 90 degrees, how much will dissolve? Let's see. Here's 90 degrees. I have to go up to the NaCl line and go across, and this is where the line would go across, so we see that it's 40 grams. What about NaCl or HCl? Let's look at HCl. That says 67 grams. How do we get that answer? Let's look at the pen. Let me get another one. Green is good. And here is the HCl line right here. And I'm on my laptop, so it's really hard for me to draw it. Okay, HCl at 30 degrees. So you would meet that line, go up and across, and there is where it would go. How about NaNO3? How much dissolves at 50 degrees? You got the idea. Go on the bottom. Let's get you a new color pen. Let's go with the light blue. Everybody loves this color, cyan. I'm going to go up, 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 until we get to this line, and then you're going to go across. It's about 115 grams. You do this one by yourself. How about NH3? That is being dissolved at 10 degrees Celsius. So, where's the temperature? Go to the bottom, find 10 degrees. Go ahead, you can do it. And then, draw a line. So let's use red. 10 degrees. Where are we stopping at? NH3. Keep going until you get to NH3. NH3, 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 right here. Okay, now what do I do? Well, they want to know how much. So where's the how much part? Oh, over to the left. There we go. 70 grams. Now, here's my question for you. How much more NaNO3 dissolves at 50 degrees than NH4Cl? I'll say it again. How much more NaNO3 dissolves at 50 degrees than NH4Cl? Oh boy, this is like a two-part problem. All right, how much more would mean, do I add, subtract, multiply, divide? How much more? As soon as I hear that, I know I have to subtract. So let me find them out individually and then subtract the two. Is that what I'm supposed to do? So let's use a color pen that would discriminate this nicely for us. Let's use black because it will help us locate the lines. So I said NaNO3 at 50 degrees. How much more? Go all the way up, all the way up, all the way up, and make an X. So we know at 50 degrees, it's 115. Oh, we already did that one. Okay. And then how much more will dissolve of NaNO3 at 50 than NH4Cl? Okay, keep going up, and go across. I'm going to say that's about 52 grams. What do you think? Go across and tell me. You think that's 52? Yeah, I think it's 52. So what did we just say? How much more means we have to subtract? 52 grams. Haha. No smartboard for me. It's my fingers. I can't get the little dot there. All right. Now subtract. So 5, that's 0. This is 3. And this is 6. So we're going to get, and at 50 degrees, 63 more grams of NaNO3 to dissolve than we can get of NH4Cl. That's wonderful. You guys are amazing. All right, this is something we're going to do in class. So we're going to end the movie right now, and then you can watch the Answers and Bases. So I hope that you have all your notes done.